Okay, I will start. Can you hear me?
Yes, yes, we can hear you. Yeah.
Excellent.
Thank you.
Okay, good. So I will speak today and tomorrow about Bayesian inference. Today we'll have sort of a broad introduction, and tomorrow we will discuss some aspects of Bayesian computation, which is rather particular challenge. So let me write a little bit.
Sorry, Professor. Is it okay if someone to say some question directly, or it's better to wait until the end of the session?
You can go ahead and if you have organizing things to say, please do.
Yeah, it's okay. It's up to you.
Go ahead.
Okay, thank you. So everybody can say a question if you need. Yeah, please. Time is yours, Professor.
Okay, I will begin. Okay, so we're going to start with the derivation of what is very well known as Bayes' theorem. And then, but there's things to discuss about it. Interestingly, I'm going to go quickly here because I think Tree derived it also, or at least laid much of the foundation of it, I think on the first day when he discussed probability theory. And then I'm going to go through 5 topics and both concepts and some sort of more applied use in astronomy of Bayesian inference involving priors and posteriors and credible intervals, marginalization, and hierarchical modeling. And then I will end with a fairly sort of not confused. Well, maybe it is confused. Why don't we just say that there's no broad consensus on sort of the meaning and utility of frequentist and Bayesian approaches. And there used to be a lot of fighting, like even attacks from one group to the other in the 20th century. But those attacks are mostly over, but there are still interesting issues about when they should be used and what they're good for and what they're not so good at. And I'll give you my perspective, but other people will have other perspectives as well on these issues. So my first comment is that this is the number of journal articles per year using the word Bayesian, and it recently crossed 1,000, and now it's well over 1,000. We're now at 2022. We're almost at 2,000 a year, and this is maybe 5 or 10% of all papers in astronomy are doing Bayesian inference. It's a very big thing. The blue curve is the same curve in statistics, and it has exactly the same shape. Basically, almost nobody, only some specialists, used Bayesian statistics before about 1995. And then, boom, it went up. And the reason it went up was advances in Bayesian computation, which we'll discuss tomorrow. Because there was no good way before about 1995, roughly, to do computations of serious problems, only toy problems. So it's really quite an amazing, this is exponential growth with roughly a 6-year doubling period. Well, Bayes' theorem is technically not a theorem. And so some people call it Bayes' rule. And the reason it's not a theorem is that it doesn't need a proof. It's simply about 3 or 4 logical inferences using logic from 3 axioms. So you have to assume the axioms are true, and then boom, 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 bang, you get Bayes' theorem without proof. So what are these axioms? And again, I think we heard them from Tree. First is, this is very abstract mathematics, okay? These are axioms of probability theory. For an event A, the probability, P is probability of A, is between 0 and 1. There's something called a sample space omega, and the probability of the entire space is 1. And for mutually exclusive events, A1, A2, A3, like that, the union of them is also equal to the sum of their individual probabilities because they are independent of each other. So this U means union or. The upside down U means and the vertical line we'll see on the next slide means given or conditioned upon. So here, for instance, is just a little diagram of the sample space and two different events and their union. Sorry, their intersection is here, and the union is the whole thing. Okay. So then there's a concept, a very important concept, a definition called conditional probability. It's the probability of event A given event B. Probability of A given event B is equal to the intersection of probability of A and B. They both have to occur, normalized by the probability of B. And this is just an equation, so you can just put this on the other side of the equation and switch it this way, and you get this relation here. Okay. So let's think of it as astronomers for just a minute. The conditional probability that a star has 1 solar mass and is orbited by a Jovian planet with ellipticity around 0.5 is equal to the product of the probability that it is a G star with mass 1, which ends up to be about 2%, and the probability that a G star has an elliptical Jovian planet, which, as far as we can determine from the Kepler mission, is about 20%. So the conditional probability of both events is the product of these two quantities, and about it's 0.4%. The probability of A and B being both true. Okay. So this can be extended to more and more objects, and you get these probabilities. It's called the multiplication rule. That you multiply these conditional probabilities together if you have a whole bunch of events you want to have happen simultaneously. Okay. So let's go down in this page at the bottom. We'll get to Bayes' theorem. So let's let these B1, B2, B3, Bk be a partition of the sample space, omega, that fills the sample space. And if A is an event in omega, then to compute the probability of A, we can use the probabilities of A being in each one of the B sort of segments or partitions and add them together. This is called the law of total probability. The probability of A in the whole sample space is the probability of A given the first, that A lies in the first partition times the probability of the first partition, plus the probability of the second, the third, up to the kth partition. So now this is the trick. It's just arithmetic on these equations, okay? But the trick is to invert the equation to ask a different question. For k possible outcomes, k places in the sample space, use both this law and this one and do some arithmetic, multiplying and canceling and stuff. And you get the and put on the left-hand side the probability of the ith partition given the event A. It's equal to the probability of A given the ith partition times the probability of the ith partition. That's the conditional probability part, divided by this probability of A, this long sum here that normalizes this numerator to the full sample space. So, arithmetic using logic. The tricky thing of what statisticians did, and this started, well, it started with a man named Reverend Thomas Bayes in the 1700s, but it really was Pierre-Simon Laplace in the early 1800s who wrote a book on these things. He then reinterpreted the meaning of B and A so that it can be used for experiments, for understanding real life situations. Okay, so now I'm going to, it's just the same thing as before, except the B's is now this M and the A is now these X's. That's all I did. It's the same thing. So now we're just going to interpret things a particular way. We're going to let the X represent a data set, not just one event, but a whole collection of data. It could be multivariate, it could be continuous, it could be points, it could be single scalar numbers, it could be anything. And we're going to say M sub I is the ith model. We're going to say the partition of the sample space involves models. And the models depend on parameters theta. Theta, it can be a vector, could have 10 parameters in it. 10 scalars in this vector theta, or some other number. So the models depend on parameters. We're asking what's the probability of a certain model given the data? And now we're going to give some names to this. This one on the left is here. It's the conditional probability of the ith model given the data. We're going to call that the posterior probability density. This one here is the conditional probability of the data given the model. It's the opposite. We're going to call that the likelihood function. This term here is the probability of the marginal probability, the marginal probability, also called the prior probability of the model without any reference to it, to the data. And we're going to call that the prior information or the prior distribution. It involves nothing but probabilities and thetas and a formula of the model, but doesn't involve the data. And then this denominator, we often, not always, often will just ignore it as just a normalizing constant. But sometimes we actually use it. And I have an example where we're using it and it's just coming up in a slide. So let me say this now in sort of English instead of mathematics. The posterior distribution of a chosen model given the data is proportional to the normalized, that's the denominator, product of the likelihood of the data for that model times the prior probability that the model is true without reference to the data. Now it ends up that this likelihood, the conditional probability of the data given a model, is exactly what R.A. Fisher was talking about, starting with 1916. And when he says, I'm going to try to convince everyone in the 20th century, and he did, to do maximum likelihood estimation, this is the probability that he was maximizing. So both maximum likelihood estimation and Bayesian inference using Bayes' theorem both rely on the same likelihood. And you have the same challenge of, for your particular experiment or situation or astrophysics, to figure out a good likelihood, to figure out what the parameters it depends on. But instead of just maximizing this quantity, we are weighting or multiplying, scaling, weighting this probability, likelihood of the data given the model by the probability of that particular model. And in order to do the full calculation, we have to do this calculation for all values of theta. And if theta is in 10, there's 10 different elements to the vector, that's a 10-dimensional space. And in principle, I have to go from minus infinity to plus infinity in 10 dimensions, which of course is impossible. But it could be, this is a very large space. And at every location, or at least a reasonably dense grid in that location, in that space, I have to compute the prior probability and the likelihood. Now, if the likelihood is just like a Gaussian or something simple, this is one of these linear models, it may be very quick to compute. And you can compute 1 million of these fairly easily and do a grid in 10 dimensions reasonably well. Oh, I'm sorry. But it's also possible that it is computationally not feasible. Because what if it's a 100-dimensional model? You just can't cover 100 dimensions and do a grid on it. It's just not feasible. And what if the probability is a very complicated function requiring extensive calculation? And you can't even do 1 million of them at all. So this was the problem why use of Bayes' theorem did not sort of go anywhere until the 1990s. When first there were bigger and better computers than the past. There were no computers until the 1960s, really. And also there were better strategies. Instead of a grid across the 10 dimensions, there were strategies of optimizing this calculation. And that's what we're going to discuss tomorrow, are the strategies for computing the numerator of Bayes' theorem. So, any questions or comments so far? Bayes' theorem. Okay, let's go on to something that's sort of new. Okay. Okay, so Bayesian inference addresses modeling of data with a mathematical model. You need to have a likelihood. You need a model for the situation that you're involved in. And therefore, it doesn't involve many of the things that statistics also does. It's not involved in reducing the data from a terabyte down to a kilobyte. It's not involved with characterizing it non-parametrically, sort of graphical characterizations or looking at an image or a spectrum. It's not involved with visualization of multivariate data or anything like this. There's a lot of it not involved in certain transformations that are model-free. So for instance, the Fourier transform. You can take a data set and do a Fourier transform and then look at it and maybe even fiddle with it and then do an inverse and you get your data back. Maybe you've changed it a bit, improved it maybe. But that did not involve a model. The wavelet transform, there's no model there. A model is linear regression. There's a model. And so it's often used for regression type problems. And there is a technical field of Bayesian nonparametrics that actually has infinite dimensional parameter spaces. And Gaussian processes is actually one of these, can be viewed as a Bayesian nonparametric method with very, it doesn't have to be infinite, but extremely large parameter spaces. Generally speaking, Bayesian inference is a parametric inferential procedure. That means that you know or guess the mathematical model in advance, linear, exponential, isothermal sphere, lambda CDM model. You know the model in advance you want to discuss, you want to compare to your data. And this is the new thing about, that was true for MLE, you had to know the model to write the likelihood. But now the distribution of parameters must be known before you do your experiment, before you look at your data. And that is the new part of Bayesian inference compared to maximum likelihood. So Bayesian inference, assesses the degree to which a given data set is consistent with a chosen model. Correct models gain evidence as you collect more data. So because it's the product of the prior and this data-based likelihood, if you have very little data, the prior sort of wins and dominates the calculation, and you didn't learn very much because you don't have much data. When you have a great deal of data, the data likelihood wins, and it doesn't really matter what you put in for the posterior very much, unless you did something totally weird. And so a lot depends on your data set size and sort of how powerful the data are in confining the model in a small region of the parameter space. So the priors tend to be dominant for small data sets, and the data likelihoods tend to dominate for large data sets, not always, but more or less, it's usually true. So now here's a philosophical point, and this is the one that caused the big fights. And there were several things that caused the fights in the 20th century, but the one that R.A. Fisher hated, and I'm not saying he was right, okay, but he hated the fact that Bayes' theorem does probabilities on models and treats data as fixed. So if you're a scientist who views your data as definitive, I measured it, it's true. And the model, well, I'm not quite sure how to interpret it. Maybe this model, maybe that, I'm not sure what the parameters are. Then philosophically, you're a Bayesian. And there's a famous line from a physicist, particle physicist named Robert Cousins. Why aren't all physicists Bayesian? Because we built our experiments and we believe in our data is true, but we're not sure how to interpret them. So that's a Bayesian type approach to inference. Whereas Fisher's approach is the opposite. Okay. In that case, the model is fixed. It's a linear model. It's just a linear model, or it's a isothermal sphere model or something. And the model is fixed, and I don't fiddle with the model except for the different parameters inside of it. But I think of the data as being sort of a little tentative. And I think of resampling the data or doing the experiment over and over again. Even if I can't actually do it over again, I sort of pretend I can do it. And a lot of the statistics of Fisherian frequentist statistics is based on the concept of repeated experiments, which may not be feasible, but it's an interesting way of thinking of things. So the fact that these are two very different ways of thinking about science, and for me personally, I'm a little confused. I'm not sure I have a favorite. Okay. And a lot of statisticians today don't think much about the philosophy. They simply say, well, look, if you have prior information, let's be Bayesian. If you don't, well, let's try MLE. and they sort of adapt. Oh, and if it's Fourier transforms, then there's no modeling at all. They just adapt their method to the problem at hand. And if it's a Bayesian type problem, then there'll be Bayesians that day, and tomorrow there'll be frequentists. And the next day they'll do visualization. So the philosophy, you don't necessarily have to decide on the philosophy. Sort of like quantum mechanics. You don't have to decide on, the wave particle duality of, is it a wave or a particle? You can just say, look, the Schrodinger equation is a good equation, let's use it, and not try to figure out what it means. Okay. So this is the same statement again, that Bayesian inference is called the theory of inverse probability, because you've inverted the older thing, which is the probability of the data given the model. Now you're inverting it to estimate the probability of the model given the data. Inverse probability. Laplace loved it. Fisher didn't. Many people like it today, but it's also generally more difficult, more complex, both conceptually and computation. Now, a lot of the fighting was about this prior distribution. Not just one, it may have 10 parameters and 10 prior distributions. And the question is, do you know them in advance confidently, reliably? Now, you might, especially if you're an astrophysicist, you might know something from theory that theoretical model has very strong limitations on some of the parameters. For instance, an orbit of a planet around a star. I know the ellipticity is between 0 and 1. It can't possibly be less than 0 or greater than 1. I know that the brightness of a source in my image is positive. It can't be negative. I know the mass of a star. Not only does it have to be positive, but if it's a bright star, it has to have a mass greater than 0.08 solar masses, because that's the brown dwarf limit, known from astrophysics. And the mass of a star cannot be more than roughly 150 solar masses, or it's unstable. They're not sure about that number. And not only that, but there's something called the initial mass function for stars. It seems to be almost universal in our galaxy, at least, and maybe most other galaxies. And that means we may even know the distribution of masses ahead of time. It's called the IMF, initial mass function of stars. It's a log normal with a power law tail. And the papers that define it have thousands of citations because everyone in stellar astronomy and galactic astronomy uses it, the IMF. So those are cases where we actually know a lot about the prior probabilities of stars, planets. Now, there are other things we may not know much. And we say, well, we'll just call it uniform. We don't really know. Those are called non-informative priors, and we'll get into that shortly. And then here's my comment that before about 1995, we didn't have big enough computers, and we didn't have the right Monte Carlo techniques for simulating posteriors for high dimensional model spaces. Okay. But even today, Bayesian calculations can be very difficult computationally. It depends on the problem. Sometimes they're easy, sometimes they're hard. Okay, let's do one simple example. I think this is 2 slides. Okay, and this is a case where the denominator is crucial to the inference. Okay, I invented this one. I hope it's right. Okay, so we're going to ask a question. Okay, then I go with the telescope and I say, oh, look, there's a quasar, an active galactic nucleus, a new one. I wonder, is it radio loud or radio quiet? What's the probability that a new quasar, active galactic nucleus, will be radio loud? Okay. So in this case, my variable is a very simple variable called a binary variable. Yes, it's radio loud. No, it's not. That's it. 1, 0. Okay. And let theta be a parameter. That theta 1 means yes, and theta 2 means no. Okay. From previous surveys, I read the literature with radio telescopes and optical telescope surveys and stuff. The astronomer finds out that the probability of radio loudness, that the probability that theta is theta 1, is about 1 in 10, 1/10. So this is the prior distribution for this problem. It's a delta function. It's a constant. Maybe I could choose a 0.05 to 0.15, a little range in there. But at the moment, I'm just going to do a delta function. So now the new AGN is observed with a radio telescope, but a telescope is not perfectly sensitive. It's sensitive this particular distance and this particular whatever telescope and exposure time. I'm sensitive to radio loudness 80% of the time. So the probability that it actually is measured to be radio loud when it is radio loud is only 80%. But darn it, there's another problem. You might call it a false positive problem. 30% of the time, the telescope is going to detect radio emission, but it's not from the AGN, it's not from the black hole. It's from star formation in the host galaxy. So the probability of detecting radio emission when it is not radio loud AGN is 30%. So this is the true recovery rate. This is the false positive rate. So now we can use Bayes' theorem to calculate the chances that an AGN with detected radio emission is truly a radio loud AGN. The probability that it is truly an yes when we measure yes is the likelihood, the probability of x1 equals 1 given theta equals 1. The probability x equals 1 is 0.8. There it is. That's the likelihood. Okay. Times the prior probability, the probability that theta is actually theta 1 without any data is 10% from prior knowledge. And then in the denominator, I have to put in this big sum. In this case, it has two terms. It's 0.8 times 0.1, the same as there. And then this is the tricky one. It's 0.3 of the 90% that are not. It's 30% of them are going to show up, and the sum of the marginal probabilities. And I do this multiplication, I do this division, I come up with 23%. Oh no, this is a terrible situation. Only 23% of the true radio loud AGNs are clearly identified in my survey. 77% are either false negatives or false positives. I didn't detect it when it was true, or I detected something when it wasn't true. Oh no. So in this particular case, I can fiddle with these assumptions and try to juggle things around. I find out that the result is a little moderately sensitive to the prior, but it's mostly sensitive to this 0.3 down here, the false positive fraction. So for instance, if I could reduce the false positive fraction to 5%, maybe by doing other measurements, something like the morphology of it, is it a blue host galaxy? I might think it's star formation. Or polarization, which will show up if it's an AGM, but not if it's thermal emission from a host galaxy. Maybe I could push this down to 5% with other observations. So now if I put in 5% there, wow, this probability goes to 95%. So we just used Bayes' theorem to help us design an experiment. I'm ready to go to a radio telescope to write a proposal to Australia, to VLA in America, maybe to ALMA in Chile, and say, dear radio telescope, TAC, Telescope Allocation Committee, I want to observe these things, and I've used the Bayes theorem, and I'm pretty sure I'm going to have 95% recovery rate. And they'll say, oh, Eric, you're such a good experiment. We'll give you the telescope time. If I told them I only had 23% chance, they maybe wouldn't give me the telescope time. It's too valuable. So this is a toy problem. Usually statisticians use toy problems using coins or rolling dice. I gave you a toy problem involving quasars. Okay, so now I'll stop. What do you think of my general comments about Bayesian inference and then my toy problem?
Is there any question from the participants? No, no question. Well, if there is no question, maybe I will ask you some question.
Thank you.
In the past, I did some regression work, non-linear regression work, to separate interstellar and intrinsic polarization from stars.
Okay.
It seems similar to the your problem. It's not similar, but analogous to your problem. So I wonder what is the difference between this Bayesian inference and the nonlinear regression. Can you give some difference?
Okay, I think the main difference is this prior. If you have a nonlinear model, you have some data, and you fit it by either least squares or maximum likelihood, you are doing something that dates back to 1800 and was built and improved by R.A. Fisher around 1920. And this is the way most of us do regression in all of the sciences.
Yeah.
We have our data, we have our model, we're going to maximize the likelihood or minimize the sum of the square residuals. That's the way we do it.
Yeah.
And we've been doing it for 200 years, and we're generally pretty happy. So I suggest the only time you should be a Bayesian is if you want to incorporate prior information that's sort of meaningful, informative. So now you say, well, I'm going to make a measurement right next to my star, right next to my star, and I'm going to measure the interstellar medium there. And that's going to give me prior information of the interstellar medium that's going to go to my star. And oh, that's going to be very valuable information. And that's going to improve my effort to do the regression that I'm interested in, which is about the star. I don't care about the junk in between.
Yeah.
So you can improve by using meaningful prior information, often improve it greatly.
Oh, okay. Thank you. Thank you, Professor.
That's why Bayesian inference, in my opinion, is so powerful. For very complicated problems where you can't, the likelihood is just flopping around in 10 dimensions, you just can't do it. But with prior constraints that you have confidence in, that they apply to your problem, then it focuses the calculation in. And you get a very, very nice posterior that scientifically, wow, now I learned a lot about my stars. Okay, so that's my opinion. You will find other people talk about the philosophy and talk about other things. But in my opinion, the crucial difference is prior information that you have and you want to use.
Okay, thank you. So there is other participants who already raised hand. Please, Arifin, you can ask your question.
Hello, am I audible?
Yes, okay.
Thank you for the opportunities. So Dr. Eric, because the way you explained the problem earlier, there's so many sensitivity of the server and stuff. Is there a way to encapsulate all that factors into, let's say, a base factor or a base, I don't know, coefficient? Let's say, oh, this survey or this studies have a base coefficient this much. So we intuitively know, oh, it's quite good, it's not good, or it's quite impossible to factorize it into a simple coefficient.
I would sort of say, if you get something simple, like a odds ratio, it's only after doing a lot of calculation. Now, I made a very simple problem here, Arifin, that only had two possibilities, yes and no, and it was not a very difficult model. So I could do the calculation explicitly with using arithmetic, but that's a toy problem. it was a realistic toy problem, but it was a toy problem. More commonly, you have complicated noisy data and you have complicated models. Models may even have nuisance variables. We'll talk about them in a few minutes. And there are all sorts of problems. And to say that it's simple, it's not simple. You have to do a computation over the space to get the posteriors. Now, it could be, for instance, you can make odds ratios afterwards that are simple. But at the beginning, I don't think it's simple.
Okay, thank you, Doctor.
Okay, thank you. I saw Abdullah also raise hand. Do you want to ask something? Abdullah?
Yes, I have a question. Hello, Dr. Eric. I just have a question about the toy project, and when you multiply by 0.05, like 5%, and this and we saw like how this changed the value from 23% to 95. But like when we assume that like 5%, it's maybe the morphology or other parameters, is that maybe we can say it is manipulating the equation, or maybe the morphology itself, it is not a blazar, it should be maybe sometimes supernovae or other like objects?
Interesting questions, Abdullah. This is the kind of judgments that is a scientific judgment. Is my prior information really relevant to this problem? Does my data have a supernova that's an outlier of a completely different cause that will mess up my decision, my decision process, my estimation of parameters? All I would say is that not everything involved is for the statistician. Some of it is for you. You're the astronomer. And that's why you might do it once, and then you might take out a bad point you don't think it's right and try it again. You might do it first with one prior and then wonder if that prior may have biased it. Try another reasonable prior. In fact, that's advised to try different priors and see whether your result changes a lot. And then you have to write a paper. Then that's your business. The statistician does not help you write the paper. Okay, so there's both statistical aspects, but also scientific aspects.
Okay, thank you very much, Professor.
Right.
Okay, thank you. It seems no more raised hands. So Professor, you can continue your lecture.
Okay, so now I'm gonna have a bunch of slides that are a little more technical, but not too technical, about the specific sort of aspects of using Bayes' theorem for astronomy, okay? So let's have a few slides on the prior, okay? First, I'll talk about uninformative priors, okay? So a lot of Bayesian studies in astronomy, and particularly in social science, okay, they don't really have an empirical basis for specifying the distribution of the third parameter, okay, in advance of the data, okay? So they just say, well, we'll just put in a uniform prior, something that's uninformative, okay? Like 1, uniform means the number 1, okay? Now, in the 20th century, there was actually a certain procedure, something called conjugate priors, that if you had these models, Pareto is power law, you would put in these priors. And the reason they did it was that it helps analytical math. Things divide out and the math became easy when you only had pencil and paper. But now that we have computers and MCMC algorithms, we don't care very much about conjugate priors. So you might see this in books, but most people don't use them anymore. Okay. So more interestingly are the two common choices. One is the uniform distribution over, well, it's either the full space of possible values, or maybe you have some astronomy reason to say, well, there's a uniform distribution between 0.3 and 0.7, because I'm pretty sure it's never going to be less than 0.3 or greater than 0.7, but I don't really know. I'll just make a square, a box, uniform between 0.3 and 0.7. That's very common, okay? Now, the interesting thing is that if you put in unity 1, into Bayes' theorem, if you put 1 in for the prior, just the number 1, this just becomes the likelihood. So the posterior becomes the likelihood divided by a normalizing constant. So instead of a posterior surface, you get a likelihood surface. They're the same. So when astronomers use uniform uninformative priors, they often are simply doing MLE. Nothing wrong with that, but frankly, they should say so. They should say, well, it's a very uninformative prior. I'm really maximizing the likelihood. That's not exactly the same, because if you make the likelihood, the range of the one very small, it may not be exactly the same, but more or less, uniform priors give MLEs most of the time. And many astronomers don't seem to know this. I'm an editor. I see many papers. And I see people saying, oh, I'm going to do a Bayesian calculation. They put Bayesian in the title sometimes. And then they use uniform priors for all of the parameters. And I say, why don't you just say you're doing MLE? And why don't you use the EM algorithm, which has a theorem of convergence instead of MCMC that doesn't have a theorem? You might do it in 100, maximize it in 100 iterations with EM algorithm instead of 1,000,000 iterations with MCMC, but you don't even know you converged. So a lot of astronomers don't realize that they're actually doing MLE. And another way of phrasing it is that the fight between frequentist and Bayesian is not such a big fight. There are many frequentist solutions that are Bayesian with simple priors. And Bayesian solutions that have unity for the prior are often MLEs. They're not really enemies. They're cousins, sisters, and brothers. That's my opinion. I don't think they're so different if you have uninformative priors. Now, another one is the Jeffreys prior. This was invented in the middle of the century by a geophysicist named Harold Jeffreys, very brilliant man. And it is the square root of the determinant of the Fisher information matrix. I won't go into it, but this particular choice ends up to have certain virtues in likelihood theory. Now, it's important not to use an improper prior. Now, another way of phrasing it is that everything here, this, must all integrate to 1. They must be PDFs, probability density functions integrating to 1. And if they don't integrate to 1, because you didn't normalize it, right? It's called improper, particularly if it integrates to infinity. And that's really bad. Okay, then your calculation could be incorrect. And my colleague Hyun-Sung Tak recently wrote a monthly notices paper that about 1/3 of the astronomy papers were using improper priors. And ends up, this is very easy to fix. Just put a range on your uniform prior, and it won't be improper anymore. So this is like a silly mistake rather than something very serious. But more seriously, and why many statisticians didn't like Bayesian approaches, is that the prior choice seems arbitrary sometimes. Now, let me give you an example. If you even choose a uniform prior, did you make it uniform in X or uniform in log X? It's not the same. You get a different answer. You actually get a different posterior, even though they seem very similar. For the normal model, normal means Gaussian, there is a debate. Do you do a prior of a uniform variance or uniform standard deviation? The variance is the square of the standard deviation. So it's like a square root instead of a log. What do? Well, it ends up, if you take a uniform standard deviation, the Bayesian calculations give you the same calculations that you get out of MLE. But how do you really know So the word arbitrary comes in here. If you're making arbitrary prior choices, they could affect your result. It will affect it, but it might affect it a little teeny bit. It doesn't matter, but it could affect it a lot. That's why you should check different priors, unless you have scientific priors, informative priors, and then you're relying on that. So this page, I'm not sure I'm going to read this all. Okay. So I personally discourage uniform or uninformative priors, particularly improper priors are just wrong. Okay. And uninformative ones, if they're uniform, you might as well just say it's MLE. That's my opinion. But you can go ahead and make a map of the likelihood surface, a map of the chi-squared surface, or a residual sum of square surface for least squares, or a map of the posterior surface. Those maps are still there. They're still useful. You don't only have to find the maximum. So they're actually rather similar. Bayesian inference and frequentist inference are often rather similar. Okay. If you do a Bayesian analysis, you should publish the prior distributions in a table. Each one of the 10 parameters tell us what the distributions that you assumed. Okay. And when inside of it, you should say, and I tested all other priors and it didn't seem to matter. If I test other priors and the science result flops around, you're in trouble. Maybe your data is very weak. And it depends only on arbitrary choices of priors, then that's not, you shouldn't publish. So here are two comments. This one is by a British statistician who wrote a very fine book. And he's sort of against it. He's sort of an anti-Bayesian. I just thought I'd give you the quote just so you can read it, okay? Because the prior is inescapably part of the model of the Bayesian approach. All these things that one does are inescapably sensitive to the choice of prior. In consequence, it's only when the priors that differ between the models are really precise priors and meaningful priors can we justify using Bayes factors, posteriors, and things like this. Okay? And then, like the marginals, there's some details in here that I'm not going to cover. So it just means you got to have good priors to be a good Bayesian. And here is the issue by my colleague Tak. That's 3 statisticians writing in the Astronomy Journal just recently. Okay. Jointly proper priors guarantee that the posterior is proper based on theory, on theorems. Okay. But when researchers want to adopt improper priors, even if they're physically motivated, then it's hard to feel that your posterior is correct. So it's a useful practice to adopt proper priors that can mimic the behavior of the improper ones. So astronomers aren't subtle enough about normalizing their priors sometimes. And so this is important, even if it's a scientifically motivated prior. Okay, let's now move to posteriors. So posteriors is what generally you want. It's the results. It's the left-hand side. It's the probability of your model given your data. Okay. And we often plot projections of the posterior. If it's just univariate, we can just plot it. This is the data. The data are these black dots here. And this is the model in green. It happens to be a mixture model. It has a purple component and an orange component. And so it was a complicated 2-component nonlinear model fitted to this small data set. This happens to be a model of Sunyaev-Zeldovich distortion to the cosmic microwave background spectrum, taking dust into effect, applied to 26,000 galaxy clusters from the Sloan discussion. It's pretty complicated, okay? Even though it looks like there's only 6 data points here. In fact, there's really thousands and thousands of data. that go into this. And the model is fairly complicated, having two components, cosmic and dust. And now we're going to look around that model you're looking at is the brightest point in this diagram here in the lower right. And now this is a plot around it, around data of 2.05 and temperature of 21 degrees Kelvin and some other constant. I don't know what these parameters are, some sort of parameters. And what you're seeing here is sort of an idea of how the parameters depend on each other. Like these two seem to depend on each other pretty strongly. And these two are sort of round and they don't depend, they're independent of each other. So you learn things by making these diagrams. Statisticians call them pair plots, and astronomers call them a corner diagram. I don't know why, but they're useful, and as well as reporting and showing the best fit, which is a single point here in the middle. So this is a rather simple case, okay, with a very nice simple posterior. Now I'm going to give you a couple messier cases, okay? So now this is, again, some paper I found in the literature having to do with ionization and metallicity of ionized regions in the galaxy, H2 regions are called. And in the top panel here, these top panels, I'm only using 2 emission lines. And my goal is to find the posterior of some sort of some oxygen abundance and some ionization parameter, Q, it's called. Okay. So I have only 2 data points. I have a sample, but I only measured 2 lines. And the posterior says, well, your oxygen ratio has to be around 8.5, but it could be 9 or even 9.5. And your ionization parameter could be almost anything. You didn't learn, all you learned is the oxygen is not down here around 8 or 7. But you didn't learn very much. It's a very ugly posterior. It's not centered anywhere nice. It's not round. So the reason I chose this study is he showed a lousy case where you didn't learn, look, you learned nothing about the cube. And then he said, I actually have 8 emission lines, not 2. Now I'm going to run my astrophysical model with 8 emission lines and ask what's the oxygen abundance and the ionization parameter. And now it's very strongly constrained to be a rather narrow region here, with the best value is here. And this ellipse represents, I don't know, 95% or something of the allowed parameter range. And now the oxygen abundance is fairly well constrained, but also Q is constrained. And this obviously is a much better situation than this one up here. So more data helps. This is true for likelihoods in MLE, and it's true for Bayesian. More data helps, okay? But I like the fact that we can compare these 2 situations for the same problem, science problem, and the same data set. Here is another sort of messy one, okay? This is something in observational cosmology. High redshift, metal poor, damped Lyman alpha absorption systems. And we're interested in a mass parameter, some sort of a energy and ergs, and some sort of a mixing parameter. And it looks to me like the only one we learned anything about is this mass. The mass is fairly well constrained to be right about in here. But the energy, is very uncertain. And the mixing, we learned nothing. So you want my opinion? This is highly informative. What did we learn from our experiment? We learned very good constraints on this parameter. Theta 1, we'll call it called mass. We learned something about theta 2, some energy. And we learned nothing about theta 3, something called mixing. We have to go back and do some other experiment if we really want to understand mixing. So what are the advantages of a thoughtful, likelihood-based analysis like this? This could be likelihoods or posteriors. There's nothing really Bayesian about this graph. What I like about it is how thoughtful it is. That you can figure out what you learned and what you didn't learn from likelihood-based modeling. That's the modern way of doing modern statistics. Likely MLE or Bayesian. That depends on whether you have a good prior. It's really nice. I've showed this kind of stuff to statisticians. And they normally don't see these scatter plots like this. And I say, but you learn so much. And they say, well, I deal with sociologists. They don't have anything. They don't understand anything. They don't even have good questions. Their models are linear models or something, this sort of silly stuff. So this can be done only by physical scientists who really think they understand the astrophysics of what they're looking at. And here I just chose another one that just goes to show that this one is 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 parameter model. I'm sure it's very nonlinear. And this is the posterior after a long calculation, probably because it's a 17-dimensional space. And you can see that most of them are fairly well confined, but some of them fell off the edge of the graph. They didn't make the space big enough. But still, it's pretty interesting. You can do a 17-dimensional posterior. There it is. Now, let's take a simple one. There's my simple one. Okay. What do you want to report in your conclusions? I want to report beta equals 2.02 plus or minus 0.08. That's what I want to report, because that's my result that every astronomer is going to understand. They're not going to understand all of the things I did or this graph. They're going to want to see a scalar number or the beta number. So how do you get a scalar out of a multidimensional posterior? Well, you can choose the mean of this distribution. Okay, there it is. There's the mean. Beta is right there. There's the mean. Or you can take the mode. The mode is the maximum. Maximum. That's like MLE. Yes, that's right. If you have uniform priors, the mode is the MLE, the maximum likelihood estimate. So I could choose the mode. Or I could choose the median. It's a little more robust against asymmetries and non-Gaussianity. In this simple case, the mean, the mode, and the median are basically the same number. It doesn't matter. But in this case, look at this. See, the middle of the distribution may be the median, but the mode is over here. Ooh, what do I do? Which one? Well, that's why they have these different lines here. They don't quite know what to do. And guess what? I don't know what to do either. Okay. So unlike maximum likelihood estimation, where the word maximum means the mode, there's no consistent advice from the statistician on how to summarize the posterior as a scalar. And so some astronomers say, well, my maximum is this. Some say my median is that. And some say my mean is that. And it's a little bit of a pain, because how do you compare the different studies and how do you judge? Maybe you should give all three of them and let the reader decide. There's no answer to this question. Or, excuse me, there is an answer, but it depends on something called cost functions that are extraneous, and astronomers don't really have cost functions. I've asked several experts. I'm not a real expert in England and elsewhere. Cornell. I said, what's the cost function for an astronomy model, astrophysical modeling? And nobody can figure it out. So I asked all my experts, I said, what would you choose, the mode, the median, or the mean? One refused to answer, the other said median. So I sort of prefer the median, but I don't have a clear reason to do that. Okay. So that's a problem about how to report your answer. Your real answer is the function. That graph is the answer. But this is the one that you want to plot, You want to plot one of them. Is it the mean, the mode, or the median? You got to choose. And then you plot it. And then you talk about this scientifically. In other words, the meaning of best for best fit is not clear in Bayesian inference. Often it doesn't matter. They're almost the same. Okay, so what I've done so far is I've talked to you about priors. And then I talked about posteriors. And okay, I'll stop there. Priors and posteriors. Any comments or thoughts?
Is there any questions from participants?
These are the two most important things, priors and posteriors. Okay, I'll go on. I'm going to go a little faster now because it's sort of it's not unimportant, but I'm just going to go a little faster. Okay.
Okay.
So the next like 7 slides or something are just a series of other things you can do with Bayesian inference. One of them is model selection, which compares 2 alternative models. Now, this exists in MLE theory. It's called the likelihood ratio test, and there's others like it. And this is just the Bayes' version of the likelihood ratio test. So it's really the same thing, but it includes the priors. Okay, and there's an interesting question of whether you apply it to nested models or non-nested models. So the 2 models, like the same model, but one is simpler and one's more complex, and that you use the Bayes factor and the odds ratio for deciding on the complexity, or is it completely different astrophysical models? Synchrotron model for the spectrum, Bremsstrahlin model for this, completely different. Black body, completely different. Okay, so these are the ratios. This is called the Bayes factor, and then if you multiply it by the ratio of the priors, it's called the odds ratio, and the odds ratio is used for model selection. Okay, it's actually equal to the classical likelihood ratio test when you have equal priors. Okay, so but people actually prefer the Bayesian odds ratio because in classical likelihood theory from the 1930s, there it is from the 1930s, it depends which one you choose as model 1 and which one model 2. If you switch them, you get a different answer, which isn't a very good idea. So it ends up that this one, if you switch them, you get the same answer. So it's symmetrical, and that's good. It also automatically corrects for the number of parameters. You don't have to debate between the BIC and the AIC and the DIC correction. And you automatically get the BIC, and there's only one choice in Bayesian theory. And there's both simple approximate versions. The Bayesian information criteria is the approximate, and the full calculation of the Bayes factor is the and the odds ratio is the accurate one. But sometimes the approximation is perfectly good and it's very easy. Yeah. And Bayes allows non-nested models. So generally speaking, people are more pleased with hypothesis testing, comparing 2 models with Bayesian hypothesis testing than they are with frequent testing. Okay. Now, there's something called marginalization. And here I'm talking about it with respect to the Bayes factor, but you can even do it when it's not about the Bayes factor. Here, for instance, we're taking the posterior and we're integrating over one of the parameters. So it disappears from this new model here that's now a simpler model. But by integrating it, you've taken an account of the sort of the volume of the model space in that hidden dimension. And this marginalization is actually quite nice, both for Bayes factors, but also it's rather nice for getting rid of nuisance variables. For instance, maybe this scientist is not interested in the dust, only interested in the cosmic part of it. And they might marginalize over those parameters to get an improved understanding of just the cosmic parameter. If you're an observer with just an image, You might have signals and noise, and you might marginalize over your noise and get rid of it. And look only at this, it changes the error bars in particular of these things. Oh, here it is. Here's my slide on marginalization. Okay. So if you have variables or parameters of little scientific interest, like a background or something you're just not interested in, but it's in the model, you can marginalize or integrate over the nuisance variables. So here I'm marginalizing over a whole bunch of different nuisance variables, and I get a sort of a slower dimensional posterior with different properties. So it sort of averages out the influence of the other parameters. I have a friend who's very expert. His name is Tom Laredo at Cornell. He thinks that the marginalization characteristic of property of Bayesian inference is actually more important than using the prior information. But I think both are important. But the astronomers may not be marginalizing enough. This is really powerful. And hierarchical Bayesian modeling is now becoming quite popular among certain groups of astrostatisticians in astronomy. Okay. And it's sort of a little complicated. It could be that you just have a series of equations where you have y as a function of these x's, but these x's are not quite what you measure. You measure sort of u and v and w, which are functions of the x's. And so you need two equations with two sets of parameters in the model. So that's a hierarchical model. And that's used in likelihood theory as well, hierarchical models. It's a more complicated problem. You can't write it down in one equation. But also, you can actually sort of help solve the question that you don't know your priors and put parameters in your priors called prior hyperparameters. And let's say you have 7 parameters in your interesting model, but you add 3 more parameters, hyperparameters in your priors because you're not really sure what they are. And now you have a 10-dimensional problem. You solve it all together in 10 dimensions. And then you marginalize away the hyperparameters because you don't really care about them, usually. And so this is very sophisticated. It's really amazingly clever and complicated what people can do with hierarchical Bayesian modeling. And this is where the really cool work is being done. I mean, you know, when we hold a meeting of astrostatisticians, this is what they all talk about. Okay, this is quite sophisticated. I've never done it. It's too hard for me, or I don't know. But I'm very impressed on how powerful it can be sometimes to write down sophisticated astrophysical models, maybe in 2 or 3 equations in the hierarchy, and then to put in priors, but don't depend you know them, but put in some free parameters in the priors so it's more flexible. Calculate the whole thing, marginalize away what you don't like, and then try to derive your scientific insights. Ooh, beautiful work. It's really fascinating and sophisticated and powerful. This is why Bayesian modeling is increasing in astronomy. It can solve problems very elegantly and powerfully that you couldn't solve before, or at least not so well. Okay, so now I'm ready for my sort of conclusion. So since I only have 15 minutes, why don't I just go ahead and do it? And the conclusion is several slides. Okay. So first of all, there's 2 misconceptions. I just wrote this slide for you. I've never done this slide before. Okay. But this is mostly from my editing, okay, and just speaking to my friends who know more than I do. So one of my friends is Rafael de Souza and Emily Yoshida, astrostatisticians, originally from Brazil. Okay, so they talk to me about this. Okay. So a lot of people think, oh, I'm using MCMC, which we'll talk about tomorrow, and therefore I'm a Bayesian. And the answer is no. You're using MCMC because it's a highly effective optimization tool and sampling tool, a Monte Carlo tool that really works very effectively. We'll talk about it tomorrow. But there's nothing to do with Bayesian. It just helps calculate it. You can calculate it with a piece of pencil if you want to, like I did in my little toy problem. So MCMC is not essential. It's not profoundly related to Bayesian. In fact, they recommend if you have a simple posterior to use a simpler method called INLA, integrated nested Laplace approximation. That's much simpler than MCMC. It converges much quicker and is more intuitive. And basically it's fitting these posteriors. Let me get a simple posterior. There, it's fitting this with a little Gaussian or a little parabola or something. It's doing something simple and parameterizing this. And it uses that to make the computation much more easy. So MCMC is just a numerical convenience. It's important, but astronomers should now be doing INLA for many of their problems. And here's an ebook on it, and here's an article on it, a book on it. Oh, they also wrote an article on it. Raphael did. The other one is, oh, I'm making a corner plot like this. See the corner plot? It's a corner. I must be a Bayesian. No, you're making a corner plot because you're interested in looking at how what the behavior of your posterior is around the best fit. Not this is the best fit, and this is information around the best fit. But you could have done this with maximum likelihood and write this is a likelihood surface. You could have done it with least squares, and this is a sum of residual squares surface. So there's nothing intrinsic, it's just informative. It's really good to look at it, but it's not Bayesian. It's just convenient. It's good, you learn things. So pair plots and MCMC are computational conveniences, often very effective and learn a lot, but they're not related to Bayesian methodology intrinsically. Okay. So now let's go and talk about the philosophy. The classical procedures pushed by R.A. Fisher and adopted throughout the 20th century by most statisticians consider probabilities in terms of these doing the experiment over and over again, even if you can't really do it, it's hypothetical experiments. And that's why it's called frequentist, is that you're measuring something many times and look at the distribution of what you're measuring. But Bayesians take one data set, but the randomness is in the model. They're considering 1,000 models, 1,000,000 models, and principle an infinite number of models in 10 dimensions. And so they have a different idea of what they're doing. The randomness is not associated with the measurement, but with the prior beliefs and with the models used to interpret the data. So it's actually philosophically quite different. So a Bayesian views probability as the plausibility of an interpretation that combines current and past information. A frequentist views probability as the chance of a situation or interpretation, assuming many experiments were made with no awareness or interest in past information. So philosophically, they're quite different. Now here's sort of a little more subtle. A Bayesian calculation takes into account sort of the volume of parameter space, but the frequentist doesn't care. They start somewhere and they just use the EM algorithm, and they find the peak and they forget the rest. So in the analogy with thermodynamics, this is from Tom Laredo, my friend, my brilliant friend, who understands Bayesian inference better than anyone I know in astronomy. He says the Bayesian inference is sort of like the concept of heat in thermodynamics, where frequentist is like just the hottest. So they're just interested in different things. And here it is again. For a Bayesian, the data are fixed, the hypotheses vary. For a frequentist, the hypothesis is fixed and the data vary. The good news is that often it doesn't matter. They're nearly identical. Frequentist is just simpler, conceptually, simpler mathematically, and simpler computationally. And except for something trivial like the little example I gave before, Bayesian estimation is often very, very difficult computation. And in Bayesian estimation, if you got the prior wrong, it's called misspecified priors. then your posteriors are wrong. So if you don't really have confidence in your priors, don't use them. Do MLE, or just put in uniform, which is MLE. Bayesian estimation uses it far more informative. I think I have something wrong here. It basically means when you have prior information that are relevant to your experiment, like the initial mass function of stars is relevant to my experiment of looking at 1,000 stars, then it's very powerful. And it also has advantages over in the model selection. It's a technical issue, but it's often advantageous. And MCMC doesn't work. I'm saying things over and over again. Now, some disadvantages is that the inference often is a large, high-dimensional, ill-defined space of possible models. Maybe there's a possible model over there in my space, or way over there, that I didn't include in my priors, and I cannot get that. I can't get there. And for each possible model, I have to calculate the prior, and often that's a lot of calculations. Okay. It could take millions of iterations, and even then it may not converge. MLE is simpler. You're just finding the peak, then you stop. But some advantages is that when you do have prior knowledge, either from previous observations, like of stars, or from astrophysical theory, like orbits or something, if you have prior knowledge of the parameter distribution, then you can put it in, and it focuses your posterior, balancing the prior and the data in a powerful fashion. And marginalization is very effective for getting rid of nuisance variables. It can be done with frequentists, but it's not as clear. And again, model selection is better. So this is now sort of my final slide or two, my advice. I think I have a couple slides here. When you don't know very much, and you just want to ask questions like yes or no, is it a quasar or not, or radial out or not, then do something non-parametric. You have a parametric model, whether it's some power law or something astrophysical, that can reasonably be applied. And if it's solved relatively simple, then just do point estimation frequentist. Point estimation means find the maximum least squares or maximum likelihood. These are references to my textbook, our textbook. Bayesian inference is best pursued when you have external constraints and formative priors, and nuisance variables and hierarchical relationships, and it's just a messier problem. Bayesian can often tackle it better. Astronomers often do something simple like least squares. They do it in pieces. First this, then this, then this. Bayesian can often do the whole thing together, and it's more realistic, more powerful. And my opinion is, don't be an enemy to anything. Don't hesitate to do different things. On Monday, you might do non-parametrics. Let the data speak to themselves. What do the data say? What simple questions can I answer? On Tuesday, I have a model. I'm going to take my data, apply the model, find the best fit, maximum likelihood. On Wednesday, I'm going to take Bayesian with simple priors, because there's some prior information I want to incorporate. I want to see what effect it has. I'm going to do the Bayesian calculation, and I'll get a posterior. On Thursday, I'm going to do a more complicated one that has nuisance variables and prior hyperparameters I'm going to spend, and that's going to take me Thursday, Friday, Saturday, and Sunday. And on Monday, I'm going to rest. I will have done all 4 of my methods. And then I think, what did I learn from this? What did I learn from that? What was the effect of simple priors? What was the effect, the result of the full computation? And that's my last slide.
Thank you, Professor Feigelson. It's very interesting lecture. I think it is very useful for the current research. Yeah. So in the chatting room, there is one question from Alia. Her question is, should the good posterior probability always Gaussian?
Is the posterior always Gaussian?
Yeah.
I think it's sort of like the in-law approximation. The in-law approximation is approximating the posterior in a simple function like a Gaussian. And when you do that, it moves this Gaussian around and it finds the peak and it finds the shape of it and it does a nice job. But it's an approximation. In principle, every data point is creating little bumps on the likelihood in the posterior, and there could be structure there. And we saw some of those weird looking posteriors. Those are not Gaussians. You actually want a nice clean, almost Gaussian posterior, because then your mean and your mode and your median are the same. Then you can summarize it with standard deviations of the parameters, and it's all nice and simple. But in principle, it may not be simple. It might be messy.
Okay, yeah. Thank you. So Arya, are you satisfied, or you want to say something more? No? Right. There is another person raise hand. Subham.
No, Aliyah wants to ask another question. Go ahead.
Okay,
Aliyah.
okay. Please, Aliyah, you can say by yourself. Okay, Aliyah. Yes. If it is not Gaussian, should we improve by changing the choice, or should we take a conclusion from it?
Okay, the mic doesn't work. Yeah. I guess I don't know. This is sort of a more science question than a statistical question. What do I do with my posterior? Okay. Well, if it's very simple and it looks Gaussian, then there's a mean and a standard deviation mentioned, and it's very simple. You just report it like scalars. But if it's not Gaussian, your scientific answer is, well, that's it. That's what it looks like. It looks like a mess. And you have to figure out what you want to say scientifically. I think I said, well, the oxygen ratio was defined, but the other parameter was not defined in the H2 regions or something. So you have to figure out scientifically what you can infer reliably from your posterior. And I don't know. Statistician doesn't know. You're the scientist. You have to figure that out.
Okay, thank you, Professor Feigelson. So next question from Subham. Please, time is yours, Subham.
Yeah. Hello, Professor. Thank you for that informative lecture. In the last few slides, you mentioned about nuisance parameter. So can you shed some light on that?
I myself don't have that much experience doing these things, so I don't have much more to say than my general comments. Okay, but I will say that it's an interesting way to think about a modeling problem. The simplest one I like is you go to a CCD or you go to an X-ray detector or a radio interferometer. You get some sort of a signal, but it often has a noise component. Now, if you're lucky, the noise is a constant level, so then it's just an unknown constant in the model. But there might be a slope to it. The different side of your spectrum has a different number, or it could be an entire function. It could be a whole mess. And all of that background is not interesting to you because it's in your detector or in the sky or something. And you want to know about your star or your quasar. And so want to get rid of these nuisance variables, nuisance parameters as much as you can. So you put them in the model. The model has, 4 interesting science parameters and then 3 uninteresting nuisance parameters. You fit all 7 parameters together, and then you marginalize away the 3 you don't like, you're not interested in. And it takes into account, the marginalization takes into account the uncertainty induced by the uncertainty of the nuisance variables. So it sort of increases the errors on your interesting parameters correctly. That's what's nice about Bayesian marginalization, is it does the correct correction. And whereas in frequentist, you often have to think more and you may not get it right.
Thank you. Thank you, Professor.
Okay, thank you, Professor Eric Feigelson. You opened a new perspective for us in seeing astronomical data. Oh, there is another question, but the time's already limited. All right, the last question from Fisox, am I right? Fisox, please.
Hello, sir.
Yeah.
So what if the posteriors are itself correlated with each other? Will that affect our final output?
I'm sorry, I didn't quite hear it. What if the posteriors are what?
So what if the posteriors are itself correlated with each other? Not just the final
They're
data
correlated
set, but
with each other. You mean you have 2 different data sets with 2 different problems, and you have 2 different posteriors? And how do you?
No, so I mean, in the same data set, we may have different parameters, right?
Okay.
So what if the parameters are...
within a posterior, you get these ellipses or bananas, and you get this correlation. Yes, right. Right. So the maximum or the mean or whatever you choose to report is still there. So there's always a best fit. There's the maximum. Let's say it's the best fit. But then when you discuss it, you can say, well, it's not so simple. I just can't say, parameter 2 has a certain fixed uncertainty. That uncertainty depends on parameter 5 because there's a banana there and they're strongly correlated. And so I have to think, I might specifically think and talk about the scientific importance that parameter 2 and parameter 5 are strongly correlated. And maybe that's interesting scientifically. Maybe it's good news. Maybe it's bad news. I don't know. Depends on the scientific meaning of it. But it's sort of interesting to know that in maybe 3 and 7 are round and they don't depend on each other, but 2 and 5 do. And then you've learned something.
Yes. Thank you, sir.
Yeah.
Okay. Thank you very much.
Okay. So
Now
I'll see you all tomorrow for my last talk. We'll continue with Bayesian computation.
Okay, thank you. So there is
Thank you very
one
much.
more lecture from you. So from the today presentation, we will end for a short break, and then we will continue at 10 o'clock with the lecture from Dr. Trilaksmana from Space Science Institute. Yeah, thank you very much, Professor Eric Feigelson, and we'll have a break after this. Thank you very much.